team under the company runtime verification, we're taking a more classical virtual machine model based on LLVM, and that is our vision of how we should achieve interoperability with normal languages like Java and C and C++. So when you're writing smart contracts, you can write them in normal programming languages as opposed to these new wonky languages that people tend to invent that aren't really well thought out. But we're not done yet. We're big functional programming fans, so what happens when you have smart contracts that can't fail, that have billions of dollars behind them, big industries behind them like healthcare or IoT? We created a language for that called Plutus. Now normally you'd have to make a decision, where in the spectrum do I want to live? With the way we built Cardano, we can support all of them at the same time. And if it turns out that another market incumbent's pretty good, we can take it, add it to our system too. It's the magic of Cardano's control layer system and the magic of sidechains. So are we done? No! It turns out there are two other computational models that map, and we need to bring them into the Bitcoin space, to the blockchain space, because they're not actually here yet. One of them is something that Microsoft is really interested in, and they've dumped a bunch of money into it, and you know, Microsoft's a pretty bright company. And so we think we should take what they've done and make it better. And it's called verified computation. So what's that all about? Okay, so let's say Purple there. Yeah, now you're looking at me. Let's say that he has a bunch of computation he needs done. And so what he's going to do is give it to Ryan. Ryan runs a server. And he says, here you go. Here's my program. And here's some data. Go run it. And then what Ryan's going to do is he's going to run a computation and give it to Purple. Now, how does Purple know that it's done correctly? Well, he can either abstract it or he can trust it. The trust situation is he likes Ryan, I hope he's done it right, probably it's right, okay. Abstracting it is to do how we used to do calculation. In fact, it used to be a profession. It used to be called a calculator. So back at the turn of the century, 1900, 1905, if you needed to do some math, you'd walk into a room with a bunch of people, and you'd say, all right, here's the problem, go solve it, and come back in 10 minutes and say, all right, what's the answer? And whatever the majority was, you just take that. They say 64. You say, is that what everybody thinks? Okay, that's what we're going with. 64 is the answer. Thank you, calculator. That's what Ethereum does. That's basically how it works under the hood. What if, instead of doing those two things, there's something in the middle where Ryan can produce a proof of correctness. So he returns not only the output, but also the proof to Purple. And all Purple knows is the program, the input, the output, and he can see the proof, and just running the proof, which is very small, and not connected to the size of the program, he can actually verify that the output is correct. So let's say it's folding a protein. You actually verify the protein is folded correctly without redoing the work. That's called verified computation, and there's a framework for that called Pinocchio. It came out in 2014 out of Microsoft Research, and there's some follow-up papers about this. But this means that you can now run your smart contract on an untrusted server that's centralized anywhere in the world and still know that it's just as good as if you did it on a replicated virtual machine. This is the kind of innovation that you can bring into your system over time if you engage the academic world. Because the reality is that the nuts and bolts of this tech is really complicated. There's a lot going on. It involves zero-knowledge proofs and all this stuff, and it's difficult to read the papers. So most engineers aren't even aware of Pinocchio, much less have the ability to implement it. Okay? So we're exploring that. And because we're shameless thieves, we stole an employee from Microsoft Research. His name is Markov Kollweiss. He left MSR Cambridge, and now he's teaching over at University of Edinburgh at our blockchain lab. And he's setting up a dedicated lab for this research line. And over time, we're going to pull these capabilities into Cardano and make them available. But there's one other thing. There's this idea of collective problems that are private in nature. And we see them all the time. Poker is a great example. Decentralized exchange is another example. So let's take poker for a moment. Why should your card game be the concern of the entire network, of all the people there? It's not. But under the Ethereum model, and even EOS and other models, it is the concern of the entire network. It competes for resources with everyone. So how about we do this? Why don't we use the blockchain as a way to find each other and to store a little bit of information? It's called a trusted bulletin board. But do all the actual running of the game off-chain. And using something called multi-party computation. It's a shared computation that you and the other players do. And then the output of it is you can determine who won and who lost and make sure that people get their winnings and losses. But all those intermediate calculations don't settle on the blockchain. And they are off network in a private network. So they run at the speed of the game, not the speed of the cryptocurrency. But because they're connected to a blockchain and connected to assets living in a blockchain, when you do leave the system, you know you'll actually get paid. So it's a provably fair game. And it turns out that you can take this concept and abstract it to do lots of computation, private contracts in general, or even decentralized exchange. So that's the third part of computation. The first part is, let's build better virtual machines and support lots of machines because we don't know which one's going to win. The second part is, let's let people prove they've done computation correctly. And the third part is, let's let people collaborate in the short term to solve particular problems, whether that be poker or something else. So we have a lab at Tokyo Institute of Tech, and we have two people there, Mario Larangera and Bernardo David. They've been publishing papers like crazy on this topic. The first was Kaleidoscope, the second is Royale, and they have more coming. And every single one of those is an MPC protocol that will eventually pull into Cardano through something called Cardano Service Layer, which will be available to application developers to be embedded within their applications. So these really difficult things that you'd like to do, like shuffling cards or generating random numbers or Oracle services, can actually be done off-chain. And they can be done at a much lower cost than if they were replicated in a smart contract and run on a system like Ethereum. Also, it scales, because your game doesn't consume resources from the main network. It's consuming resources from the players of the game, whether that be an exchange game or that be a poker game. Okay? So, to have a great computational model, this is how you have to think. You have to have a bit of principles, so you have to have good research, and you have to have a bit of pragmatism, where you realize that maybe, just maybe, you're not going to get the idea right. And so you need to be able to borrow from the people who did get it right and move quick enough so that you can become the market standard all the same. Now, are we done yet? No! We still have that governance issue. It's a big issue. How do we resolve the issue of paying and deciding? This is a common issue every single cryptocurrency has, and there's a lot of solutions. Some of them are deeply theoretical, like Tezos, and some of them are deeply practical. Like you saw this idea of a governance system with VeChain. They did a presentation here. It's a very practical system, and I have no doubt it's going to work for them, because they understand their market, they understand their customers, and they've chosen the simplest possible way of trying to manage things with a path to improve things. So any person who thinks about blockchain-based governance has to figure out where on that spectrum they want to live. And what does that mean? So the first thing that we did is we recognized that regardless of where on that spectrum we want to live, we need a secure voting system. That's good. But we know e-voting. Our chief scientist has published papers on it for more than 15 years. It's a great topic. It's a topic I love. So we went ahead and got some people at Lancaster University. We built a whole team, and we have built a wonderful blockchain-based voting system that uses liquid democracy. This is the bedrock of our treasury system and the bedrock of our governance system. And if you're curious on how it works, we have some videos on our webs on YouTube. If you go to the iWHK YouTube channel, they're about 40, 50 minutes long, where you can see Binching explain step by step how one would go about building this. But the long and the short is, it's a delegated democracy system. So basically the idea is that representative democracy is probably not too bad, but because of resource constraints, you don't get a lot of granularity on decisions. So representative democracy is where instead of you directly voting on things, you elect someone to vote on your behalf. That's how most governments work. It's why we have presidents. It's why we have congressmen, why we have senators. But it turns out that there's a lot of cases where maybe for certain votes, they're so important, or you're a domain expert and you're more qualified than the representatives, that maybe you'd like to directly vote on it, or give your vote to a different person. And that's called liquid democracy, where you have the freedom to decide that. Either you give it to a delegate, you vote yourself, or you can switch around. So we found a way to take this system that's been around since 2002, it's a very good voting system, and take it and put it into a blockchain setting. Now, having that, we're now in a position where we can begin running experiments over an arc of time for the monetary policy of the system, and also for forking the system.